So now we'll continue on with the third video in the series, or excuse me, the third screencast. And we were looking at the diagram of the Earth, and now we'll turn our attention to the words on the top of the slide here. And it says convection and hot spots. So the Earth is very hot at the center, and it's gradually cooler as you move from the center to the surface. So the very hot center causes the heat there causes plumes or movement of hot magma to rise upward from the mantle. And then on the surface of the Earth, there are hot spots, locations between plates where molten material sometimes reaches the lithosphere. So now let's look at the theory of plate tectonics. First, the definition. The theory states that the Earth's lithosphere is divided into plates, most of which are in constant motion. Now, let's take a look at some of the evidence for this theory of plate tectonics. Let's look first at the diagram on the left, which is the globe, and you see North America, Central America, and South America, and you see Europe and Africa, and up here you see Greenland. So one of the things that first developed this idea of plate tectonics was that if you pictured this continent and this continent shifting over here, and this continent shifting toward it, you can see they almost fit together like puzzle pieces. Whoops, let me go back. So you can see this area here would fit nicely into this area here, and this little nook here. And this gradual sloping here correlates with the gradual sloping here, especially if you shift this piece called Greenland down here. So the theory was developed in 1912 by a man named Wegener. Unfortunately, Wegener was a meteorologist, and so the geologist at the time didn't want to give him credit for his theory. But over time, lots of other evidence from rocks and fossils showed us that this model, or this theory rather, holds a lot of water. So let's look first of all at one of the pieces of evidence, which is in the right-hand picture here. We have South America and Africa, and picture them slid together. There are fossils here of a freshwater reptile that have also been found here. In between, there's no fresh water, it's ocean. And it would be too far of a distance for that reptile to have migrated, let's say, from here and land all the way here. Now, it's just not just this one location. There's fossil evidence all along these coastal areas that match. So a fossil here might match a fossil here, and a fossil here might match a fossil here. That's one of the lines of evidence. Another line of evidence is rock type. Just like there's a fossil here that matches a fossil here, there's a rock type here that matches a rock type here, one here that matches this one, and one here that matches this one. In addition to the rock type, they can also now date rocks, find out how long ago a particular rock was formed. And they found that that also correlates. A rock of a certain age here correlates with a rock of a certain age there. Now, one thing about the theory of plate tectonics that is sometimes misunderstood, sometimes people figure that the plate would be the actual continent. But the plate doesn't typically, it can, but it doesn't typically run along the coastline of a continent. It can run anywhere. The plate could run like this, another plate like that, etc. So we'll take a look at that on the next slide. Okay, this is a diagram of Earth's continents and oceans and the boundaries of the plates. So for example, this orange line with dashes pointing this way and this way are spreading zones. Across the middle of the Atlantic Ocean, going right down here, is one of those big spreading zones. The one that's pushing North America this way, South America this way, Africa that way, and Eurasia that way, and Greenland that way. So this is the boundary of the plate, and you can see it's not on a coastline. And you can also see the direction shown by the arrows. Sometimes it's this way, sometimes it's a little bit that way. So let's take a look here at this boundary here. And this is along California's coast and Washington State, etc., all the way up there to Alaska. And you can see that in this case, the boundary does happen to be along a coastline, but it's not necessarily along a coastline. In fact, typically it's not. Okay, so over here to the right, we have the different types of plate boundaries and the motion of those plate boundaries. So first, A is the divergent plate boundary, and that means that the magma pushing up through here is pushing each of the plates to diverge or separate from each other. The second type of plate boundary here in B is the convergent plate boundary. And in that case, a plate boundary, let's say along an oceanic crust, for example, subducts. It goes underneath of another plate boundary when they push against one another. The third type, shown here in C, is a transform fault boundary, where when two different plates come in contact with each other, one, instead of going away from each other or diving under one another, are sliding, one sliding this way and one sliding that way, and it could also go the other way. This plate could be sliding this way, and this plate could be sliding this way, and that's called a transform fault boundary. So next we're going to look at what happens when these plates are coming into contact with one another, perhaps in a convergent plate boundary or interacting with one another as a transform fault boundary. So, first some definitions. A fault. A fault is a fracture or a break in rock across which there is movement. Earthquakes. Earthquakes occur when rocks of the lithosphere rupture unexpectedly along a fault. So you have a fault and the rocks are either pressing together or sliding around, and the pressure builds up. Eventually that pressure becomes so great, but we can't predict when it happens, so it's going to be an unexpected occurrence. And when those rocks, the pressure mounts and one gives, then you have an earthquake. The next term is epicenter. An epicenter is the exact point on the surface of the earth which is directly above the location where the rock ruptured. So in the diagram here, we have the Pacific plate moving in one direction, the North American plate moving in the other direction in a transform fault. And deep inside, the rocks give way, which is an earthquake. And the earthquake radiates out. You can see the little bullseye and then the surrounding circles. So the movement or the motion from that earthquake is felt throughout. It could be felt here, it could be felt here, it could be felt here. And the epicenter is that position on the surface of the earth, which is directly above the earthquake. So let's talk a little bit more about this very, very long fault called the San Andreas Fault in California, along which the Pacific plate is on this side and the North American plate is on the other side. The Pacific plate is moving northwest and the North American plate is sort of moving southwest. So in short, this one is moving a little bit this way and this one's moving a little bit this way. Now, I want to point out that this is a very dramatic picture. This is not really what you see in the vast majority of areas. You don't really see a ridge, a fault into which a person could walk up to it and fall in. It's simply a shaking of the ground underneath. It can be significant, but it doesn't usually separate out like that. So I'm not crazy about that picture of a fault, but so be it. I want to point out a couple of things about the measurements for earthquakes. So that's the measurement for an earthquake is called the Richter scale. It's a measure of the largest ground movement that occurs during an earthquake. Now, the thing to know about a Richter scale is that it's a logarithmic scale, just like the pH scale was. So if you have an earthquake of 4 and you're comparing it to an earthquake of 5, the earthquake of 5 is actually 10 times stronger, 10 times more movement than the earthquake of 4. If you go up another level, let's say compare an earthquake of 6 on the Richter scale to an earthquake of 4 on the Richter scale. The earthquake of magnitude 6 is actually 100 times worse than the 4. So you can start down low with, earthquakes of measuring 2 or 3, where 2, some people feel it, some people don't. 3, pretty much everybody feels it, but it's not too bad. There's just shaking. 4 starts getting significant. So let's look at some of the major earthquakes that you may have heard of. The one in California that was centered in Northridge was a 7.8. That was really high. In fact, I had a friend who lived there, and it occurred at something like 4 o'clock in the morning, middle of the night, and she was asleep in bed, and the earthquake was so strong. She actually lived in LA, not in Northridge, but it knocked her out of bed. All the lights were out because the earthquake took out the electricity, and she tried to find her way out of her apartment. She thought she went to her bedroom door, but in the dark, she ended up actually crawling into her closet. But she did eventually make her way out of the apartment, and she was okay. But that was a significant earthquake. The most recent one in Haiti, most recent big one was 7.0 earthquake, so that was significant and caused landslides. There was the one that caused a tsunami in Japan, which took out the nuclear reactor. That was a 9.0. And the most serious earthquake that I've been able to locate occurred in 1960 in Chile, and that was a 9.5 earthquake. Now, you might think that we are not at any risk of an earthquake here on Cape Cod or in Massachusetts, but in fact, though there's been no recent activity, all of us are actually on an earthquake, on faults, and there has been no movement of those faults in recent centuries, but that doesn't mean that we are immune to it, because we are on one of Boston and running southward along the south coast is one major fault, and then there are smaller faults branching out from there. So on a scale of 1 to 4, we're actually on a 3 in terms of risk for an earthquake. And one last comment about earthquakes, well, 2 last comments. One, if there is an earthquake, it's best if you can get out of a building, but maybe not under a tall tree, so that nothing falls on you. If you're stuck in a building, doorways are the strongest, and also getting under a strong table is an option, but then still get out because there are often aftershocks. And let's see, the last thing I wanted to tell you about was something that can occur when an earthquake occurs. We've talked about the Back Bay, and that the Back Bay used to be a bay, but it was filled in with soil to increase the amount of land for the Boston area. But that soil has only been sitting there for a couple hundred years, and so it's not completely settled. So sometimes when there's an earthquake, it shakes loose soil so much it actually makes it behave as though it's a liquid, and buildings can sink in, and then when the earthquake stops, it has soil which is returned to a solid state all around it. So even though Back Bay is a very expensive real estate area, I would not recommend purchasing real estate in that area for that reason. Okay, so next we will move on to the rock cycle on a different screencast.